In this video, we're going to talk about resonance structures. What are resonance structures? So, first thing, let's draw a Lewis structure for the compound, for the ion carbonate, CO3 2-. So first thing to figure out, how many total electrons is it going to need to have? It should have 24 total electrons. So if I were to draw the Lewis structure for carbonate, it would look something like this. Carbon bonded to 3 oxygens. I need to make sure that each atom satisfies the octet rule, and then I need to have 24 total. So I can move the electrons around which way, but eventually I'm probably going to end up with a structure that looks something like this. Now, one thing I want to make a note of is how do we annotate to show that the charge for the whole compound is -2? In order to do that, anytime we draw the Lewis structure for an ion, a compound with a charge, we put brackets around it and then write the overall charge in the top right corner, 2- or -2. So this would indicate that the overall charge on this whole structure here is -2. Again, we know how to get this value by calculating the formal charge on each atom. Now, if I had asked you to draw these a Lewis structure for carbonate, you might have come up with a slightly different structure. You might have come up with something that looks like this. Where, I apologize, this should be a carbon. Okay, still with a charge of -2. Now you might be looking at this and think, wait, sure, that's a completely different structure. Or you might be thinking, wait, that's the exact same thing, you just moved where the double bond was. I did. The only difference here is that the double bond that was bonded to this oxygen, we'll call this oxygen 1, 2, and 3, is now bonded to the second oxygen, here. Although they're all atoms of oxygen, each oxygen is a unique atom. So since it's a unique atom, if this oxygen has a double bond to it in this structure, but a single bond here, this is technically a different structure. Since it's a Lewis structure that looks different but is of the same compound, we call that a resonance structure. So they're Lewis structures that are different for same compound. Okay? And all we've done is we've rotated where the bonds are. The way we abbreviate or note that they're resonance structures, we put this arrow between the two. And you might also be recognizing now that, wait, sure, you could probably draw a third resonance structure. You just move the double bond to another spot. And you're absolutely right. I could move this one over here to this oxygen, still 2-, but all 3 of these would be considered resonance structures. All of them exist at the exact same time. So what does that mean? Let's say we have 100 carbonate molecules floating around. How many of them look like this? And how many of them look like this? And how many look like this? Well, since all of these structures are the same, the double bond is just in a different place, the formal charge on each atom is going to be the same. In terms of, there will be 2 oxygens with a -1 charge, these ones here, and then carbon with 0 and an oxygen with 0. It just changes which oxygen it is. So out of these 100, 1/3 of them would look like this, 1/3 of them would look like this, and 1/3 of them would look like this. They're all equivalent energetically. But let's say they weren't equivalent energetically. How could we figure out which structure is most likely to exist? Well, in order to do that, okay, we need to pay attention to 2 things. The things that we want to pay attention to, basically, how do we figure out which one is most likely to exist? 2 things you need to pay attention to. Number 1, we want the structure, the Lewis structure, with fewest formal charges, meaning the formal charge is closer to 0. We don't want formal charges of -2, -3. We want them 0, -1, +1. But also, if there are formal charges, we want the Lewis structure with the negative formal charge on the more electronegative atom, on the atom that wants that electron, that negative charge, more. So how do we apply that? Well, let's say we're given two Lewis structures for SO2. One that looks like this, and one that looks like this. How do we know which one is more likely to exist? Well, we have to apply that logic from before. We want to figure out the formal charge on each atom and see the structure with the fewest formal charges. And then if there are charges, find the Lewis structure with the negative charge on the more electronegative atom. So let's do that. Let's figure out the formal charge on each atom. So formal charge on oxygen here is going to be equal to 6 minus 6 plus 1, negative 1. For this sulfur, it's going to be equal to, and just to be clear, there should be another dot right there. This should be equal to 0. Excuse me. 6 minus 2 plus 3, which is positive 1. And here, a formal charge equal to 0. So the total formal charge, negative 1, positive 1, and 0 adds up to 0, which we should get because this is a neutral compound. But we have some formal charge. Let's see, does the other structure have any formal charge on its atoms? Well, on this oxygen, it's going to be formal charge equal to 0. Same thing here, formal charge equal to 0. And on this sulfur, it's going to be equal to 6 minus 1, 2, 3, 4 plus 1, 2, 6 equals 0. Aha! So each atom here has a formal charge of 0. Even though these are both Lewis structures, and they both have the total number of electrons, this structure is much more likely to exist because it has the fewest amount of formal charge. And by fewest amount of formal charge, I don't mean the fewest overall, because they both have the same overall amount. But on each atom has the fewest possible. There's one other thing that we need to know how to do, and that's calculate and determine something called bond order, which is related to bond length. Okay? Bond order, which I'm going to abbreviate as BO, is going to be equal to the total number of bonds in a structure divided by the number of bond locations. And by bond locations, I basically mean spaces between atoms. When we calculate bond order, we're going to get integers, things from 0 up, okay, whole number positive integers. If you calculate a bond order of a molecule to be 1, that means the molecule has an average of a single bond in the whole structure. If you calculate a bond order of 2, that indicates the structure has a double bond overall. 3, triple bond. How is this important? Well, this helps us figure out bond length. Not all bonds are the same length. Some bonds are shorter than others. Single bonds are longer. Triple bonds are shorter. And the reason for that's pretty straightforward. If we drew, a triple bond here between carbon, here's a double bond, and here's a single bond, okay? Here, we have 6 electrons, okay, pulling on those atoms, pulling them close together. Since we have more electrons, 6 of them, there's more attraction pulling these atoms together, making that bond shorter. Here, we only have 1, 2, 3, 4 electrons, so the attraction is less. And here, there's only 2 electrons, so the attraction is even shorter, which means that carbon-carbon single bond is going to be longer. Literally, if we measured its length, it would have a longer distance than a triple bond. How can we use that to do some comparative analysis? Well, let's say we have a compound like carbonate, the ion carbonate, CO3 2-. We drew the Lewis structure for it earlier. Let's just draw it again real quick. This is one of its resonance structures. Again, there are 2 others. 2 other main ones, okay? 2-. Let's say we wanted to calculate the bond order. So we know the equation is bond order equals total number of bonds divided by the number of bond locations. So the bond order, let's see, how many total bonds do I have? I have 1, 2, 3, 4. Each line counts as a bond. So I have 4 total bonds. Now, I need to divide that by the number of bond locations, which we've said is the spaces between atoms. So how many spaces between atoms do I have? Well, between this oxygen and carbon, that's 1 space. Between this oxygen and that, this carbon and that oxygen, that's another space. And between these 2 atoms, that's a 3rd space. So there's 3 potential places where bonds could exist. So we would divide it by 3. So the bond order is about 1.3. What does that mean? What's the significance of that number? We know that a bond order of 1 is a single bond. And a bond order of 2 is equal to a double bond. So if we were asked to figure out how long these bonds are, on average, the bond length in carbonate is about 1.3. So it's slightly shorter than a double bond, but longer than a single. And let's see, does that make sense based on the structure? Well, yeah, because I have 2 single bonds here, okay, and I have a double bond here. So there is some double character in this compound and some single character. So I'm going to expect it to be longer than a single because there is some double bond action going on. Let's look at another compound, CO. So if we drew the Lewis structure for CO, CO would look like this. Let's calculate the bond order for this molecule. Well, if we just look at the structure, we would expect the bond order to be equal to 3 because we have a triple bond and there's no other bonds going on. But let's prove it. So bond order is going to be equal to the total number of bonds, that's how many lines I have, 1, 2, 3, divided by the number of bond locations. How many potential places could bonds exist? How many spaces between atoms do I have? There's just 1 space right here between these atoms. So it'd be 3 divided by 1, which gives me a bond order of 3. So if I wanted to compare that to the bond order of carbonate, I would expect this bond to be longer than this bond because this bond has a larger bond order. What about one more example? CO2, carbon dioxide. Okay, here's the Lewis structure for carbon dioxide. You might think, okay, Shar, this is going to have a bond order equal to 2 because I only see double bonds. So that means the average bond is just a double bond. Again, prove it. Bond order, how many total bonds do I have? How many total lines? 2, 3, 4. How many places could bonds form? How many spaces between atoms do I have? There's 1 space. There's another space. 2 spaces. So 4 divided by 2, that gives me a bond order of 2. What we need to be able to do walking away from this video is calculate the bond order of a molecule, like this. We need to be able to compare bond lengths, where the more single bonds we have, the longer they are. The more double and triple bonds you have, the shorter they are. And you need to know how to, given a set of Lewis structures, figure out which one is more likely to exist based on the criteria that we want the ones with the fewest formal charges and the ones where the formal charge is on the negative formal charge is on the more electronegative atoms.